The three equations we start with are for average velocity, for which there are two. And we show average velocity as v bar. Average velocity can be written as in two ways. One is it's delta x over t, which is the same as x minus x naught over t. And the other way it can be written is as v, your final velocity, plus the initial velocity over 2. And then the other equation we're going to start with is the one for acceleration. Now, in algebra-based physics, we assume acceleration is constant, and that's the reason that this equation is valid. It would not be valid if acceleration was not constant, because the line connecting the beginning and the end velocity would be curved, right, if the acceleration wasn't constant. It's only because the acceleration is constant, we have a straight line, that we can use that. All right, what is acceleration? Well, acceleration is the change in velocity as a function of time, which is equal to v minus v naught over t. And that can be rewritten in this form by multiplying both sides by t and adding v naught to both sides. It can be written as v equals v naught plus at. Right? So I've got this equation a, this equation b, and I've got this equation c. I'm actually going to put a number 1 next to that, because that's actually one of our kinematics equations. As you can see, x minus x naught over t is the same as v plus v naught over 2. So I can put those two equal to, in fact it already says they're equal to one another. So what I'm going to do is say x minus x naught equals v plus v naught over 2. I've forgotten my t over here. For some reason it does. All right, so that then becomes, if I rearrange, it becomes x equals x naught plus t times v plus v naught over 2. Now, I have v in here. So what I'm going to do is substitute this one in for v. All right? So now it becomes x naught plus t v naught plus at plus v naught over 2, and that equals x naught plus, notice I have two v naughts here, v naught plus v naught, so I have 2 v naught over 2. So that becomes, if I multiply this out, just 1 v naught times t. And now I've got 1/2 of at left times t, which is a half at squared. And that's our second kinematics equation. Right? It's also useful, in fact this is a third kinematics equation here. And it's also useful because it's often the case where we don't have t. It's also useful to find a situation where we eliminate t. So using equation 1 here, I'm going to rewrite it and use it in the form of c. What I'm going to do instead is I'm going to transform c, and it's going to be t equals v minus v naught over a, right? And then substitute into equation 2 to eliminate t. So I'm going to rewrite equation 2. So I've got x equals x naught plus v naught v minus v naught over a v minus v naught over a plus 1/2 a times v minus v naught over a all squared. All right? So what I'm going to do now is I'm going to look at this and say, oh, that's a squared, right? And I can, because that's on the bottom by itself, I can actually just use that to eliminate this a and bring 1a outside. All right, so I'm going to do that. Okay. Now what I'm going to do is I'm going to multiply both sides by 2a. And I'm going to move this one over to the other side first. So it becomes x minus x naught. And I'm going to multiply both sides by 2a. And now this becomes 2 times v naught, because the a's cancel but the 2 is left. V minus v naught plus v minus v naught all squared. With this a little bit, 2v naught times v minus 2v naught squared is what that becomes equal to. So 2v naught times v minus v naught, 2v naught squared plus, and then multiplying this out, it becomes v squared plus v naught squared minus 2v naught v. The terms in v naught v cancel, and this v naught squared cancels with that too. So what I'm left with is minus v naught squared plus v squared. Right? I'm going to add v naught squared to both sides, and I'm going to invert the equation so it says v squared equals v naught squared plus 2a x minus x naught. And that is the fourth kinematics equation.